All right, test chapter 10, section 2. We're talking about, again, some stuff that we've already talked about coincidentally when we did some stuff there with radians before break, and some new vocabulary-based stuff involving the relationship between angles and arcs in a circle. So we start with something we do already know. Everyone should remember the term central angle from right before break. Again, that is an angle in a circle whose vertex lies at the center and whose sides are radii. So if we're looking at this picture, angle ABC is a central angle. Okay? Okay. So it's worth noting that this central angle does have a measurement, x degrees, whatever that is. I think I actually used theta for it before when we did arc length, but that's okay. We can use whatever variable we want. It's worth noting that that central angle intercepts an arc on that circle. Okay? And notice the notation there, AC are the endpoints of that arc on the circle. Everybody see it? Guess I should probably turn the lights out. That would probably help with seeing it. Okay, so that arc AC would be named with its endpoints, and we would use this just arc symbol over the top, sort of like a line segment symbol but curved, to indicate that it is an arc. Okay? The measure of angle ABC is x degrees, and that's also equal to the measure of arc AC. Okay? That's how central angles work. Okay, arcs, just like angles, have measurements, either in degrees or in radians. Now, we're only going to talk degrees in this chapter, because we're trying to keep it relatively introductory because we haven't done any of this before. Okay? So if that were a 48-degree angle, then the arc would be considered a 48-degree arc. Okay? If that were a 63-degree angle, this would be a 63-degree arc. The arc and the central angle are equal. Okay? Keep in mind that this is a circle, which means if we look at all of the combined central angles in a circle, assuming that none of them share any interior points, what should they add up to? It's a circle, so they should add up to 360. Okay, so in any circle, the sum of the measures of the central angles with no interior points in common is always 360 degrees. So in that picture, the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3, those three central angles make up the entire circle. So they would add up to 360 degrees. And the same thing would be true of their intercepted arcs. They would also add up to 360 degrees. So we haven't really talked about arcs. So we should probably do that. Talk about the different types of arcs. There are 3 of them. Everybody good on this page? Yes? No questions? Cool. So there are 3 types of arcs in a circle. Okay? The first type, and the one we'll use the most often, is called a minor arc. A minor arc is the shortest arc connecting 2 points on a circle. It's worth noting that minor arcs always measure less than 180 degrees. Always. And they're named using the endpoints of the arc. Okay, so just as a quick demonstration, we had ourselves a little, ooh, why is it filled? That's not happy. Let's fix that. We had ourselves a little circle. Like so. Okay, and then arc AC is a minor arc. Okay? Now, notice that the yellow arc there is not the only arc with endpoints AC. Correct? There's also this arc. That also has endpoints AC, doesn't it? But that arc is way more than 180 degrees. Yes? That arc is a major arc. A major arc would be the longest arc, connecting 2 points on a circle. Okay? When we name those, we have to have a third point on the circle. Okay? Major arcs always measure more than 180 degrees. And they are named by naming the endpoints and a third point on the arc. Okay? So for instance, I just highlighted this major arc in pink. That major arc would be named arc ADC. Okay, indicating that we started naming it at A, went through D, and ended at C. See what I'm saying? Could also be named CDA, just like angles, the names can be reversed. Okay? So, we said before that the measure of an arc is equal to its central angle. Yes? So if that central angle is x degrees, what's the measure of arc AC? It would be equal to that central angle, yes? Okay, if this angle is x degrees, then AC is x degrees. Okay? What about the major arc? How would we figure out the major arcs? Yep, go for it, Macy. Good. The major arc, ADC, would be 360 degrees minus the central angle. Okay? That's how we would figure that out, because it would be the rest of the circle. Okay. So that raises an obvious question, and that is, okay, what if the arc is 180 degrees? Well, that's something we should already be familiar with. That is a semicircle. A semicircle is an arc formed by a diameter. Okay, in other words, the endpoints of the arc are the diameter. Which means that semicircles are equal to 180 degrees. So again, let's just give a little drawing of that just to make sure we've got it. Okay, so here's our arc. Center's about right there. Let's say these points were called D and E. Semicircles also require a third point so that we know which semicircle we are talking about. So let's say this was F. DFE is a semicircle. Again, it requires 3 points because we have to state which side of the circle, which half of the circle we are talking about, the left half or the right half. Okay? And that would tell us to go from D through F and end at E. So that is a semicircle. And the measure of any semicircle is always half of the entire circle, or 180 degrees. Okay, semicircle is something we found the area of. We've probably found the circumference of a semicircle when you did composite shapes in junior high. Okay, we've seen that before. That should not be new news. Now keep in mind that if I give this center a name, let's say I call the center G, that angle DGE is what kind of angle? What do we call an angle that's equal to 180 degrees? A straight angle. Okay, this is a 180 degree angle, which is why the arc is 180 degrees, because that is a straight angle. Okay? It's one of the very few places in actual math that we see a straight angle. We never see them in polygons, but we do see them occasionally in circles, in the form of a semicircle. Okay? Okay, we're going to take that information and we're going to do some examples shortly. Here we go. Okay, so GJ is a diameter of circle K. We're supposed to identify each arc as a major arc, a minor arc, or a semicircle, and then find the measure. So we'll start with GH. Remember that there's only 2 letters there, which means that this is a minor arc. Only minor arcs can be named with 2 letters. Okay, so second that we see that there are only 2 letters there, we know that they are talking about the shortest arc between G and H, which would be the minor arc, GH. What is the measure of GH? Perfect, 122 degrees. It is equal to the central angle. Central angle is 122 degrees, so the arc is 122 degrees. Okay? That's the easy one. Any questions on the first one? Okay. So then it says, what is the measure of GLH? Well, GLH is what kind of arc? It is a major arc. It is from G through L and ending at H. So how do we find the measure of that arc? Yep. Good. 360 minus 122. The measure of the major arc here would be the rest of the circle. So that would be 360 degrees minus the 122 degrees, which is 238 degrees. Okay. Then we have our third example there. What kind of arc is GLJ? Yep, G and J are the endpoints of a diameter, which makes this a semicircle. I don't know. Okay, since GJ is a diameter, that tells us that GLJ is a semicircle, which means its measure is at 180 degrees, because all semicircles are equal to 180 degrees. Okay, I have a challenge question for you, and I want you to try this one. Okay? 1 second. Find the measure of arc HJ. Basically, we're adding a part to the problem. Okay, so HJ. First off, what kind of arc is HJ? Yep, that is a minor arc. How do we know it's a minor arc? Yep, only 2 letters. It's definitely smaller than 180 degrees. Okay. Now, how do we find the measure of HJ? Say what now? Yeah, we need to find this central angle. Well, this is a diameter, which means this angle is the supplement of 122 degrees. 180 minus 122 is what? 58? Okay? Keep in mind, again, the way I'm getting that is I'm doing 180 minus 122 degrees because those 2 angles are supplementary. So I can do 180 minus the 122. How do I know they're supplementary? How do I know they add to 180? Yeah, that's a diameter, which means this has to be a 180 degree angle. Okay, very good. Very good. Okay, so HJ's measure would be 58 degrees. Okay, good. Just wanted to see if we could figure that out. Otherwise, there might have been questions. All right, we good on this page? Yes? Yeah. Outstanding. Let's see how much more we can get in today. Okay, a little bit more vocab here. We have 2 newish terms, both of which contain words we should already know. Congruent arcs. What does congruent mean? Equal, geometrically equal, same size, same shape, yes? So those are defined as 2 or more arcs in the same or congruent circles which have the same measure. So, if the measure of angle 1 is equal to the measure of angle 2, which means angle 1 and angle 2 are congruent, then arc FG is congruent to arc HJ. Okay, arcs and angles, they have a lot of things in common. Notationally speaking, they're very similar as well. If we can state that arc FG and arc HJ are congruent minor arcs, then that means their measures are equal as well. Okay? So congruent arcs are two or more arcs, two arcs, in the same or different circles, congruent circles, which have the same measure. Okay? Then we have adjacent arcs. What does the word adjacent mean? Next to. Very good. Okay. So two arcs in a circle, and that should say which have exactly one common endpoint. Okay? They share one common endpoint. So if we're looking at that picture, we could state that arc HJ and arc JK are adjacent arcs because they share a common endpoint, point J. Okay, that brings us to the arc addition postulate, which is basically the angle addition postulate, but with arcs. Okay? States in words, the measure of an arc formed by two adjacent arcs is equal to the sum of the measures of the two arcs. So if we look at that picture, everybody see X, Y, and Z there on the circle? What we're stating here is that the measure of arc XZ is equal to the measure of arc XY plus the measure of arc YZ. Okay? If we have two adjacent arcs and we add them together, we get a bigger arc. Same exact thing we did with segments and angles all the way back in Chapter Dos in September. Fun times. Fun times. Okay, we're going to do some examples with that. Now, before we, here's a big hint for doing these kind of problems. Before you even look at which arcs you need to find all of the central angles. Do that first. That will greatly help later. Okay? So over here we've got one central angle. Actually, we have two. We have angle AFE marked as being a 63-degree angle. Yes? And we have angle DFE marked as being a right angle, meaning it measures 90 degrees. Now, it is safe to assume that F is the center of the circle. That makes AC a, what kind of line segment? That's a diameter, which means, how do we find this last little bit of an angle here? How do we find that one? Good, 180 minus 90 and 63. Okay, so if we do 180 minus 90, that's 90. And if we do 90 minus 63, we get, what's this little piece? How much is left there? 27 degrees. That is a 27-degree angle right there. Okay, now BE is also a diameter, yes? So if this angle is 63 degrees, how do I find angle AFB? Yeah, 180 minus 63, which is? Okay, 117 degrees. And then that just leaves that last little angle, BFC. But BFC and AFE are vertical angles, which means they are congruent, which makes this last piece 63 degrees. Okay, it is very helpful to know all of these angles going into this kind of problem, because then we go in here and all we have to do is find the central angle. Okay, so if we want to find the measure of arc AED, okay, arc AED, and the only reason they gave us 3 letters here was because they wanted us to make sure that we grabbed the correct arc. They could have just as easily said AD, and we should have assumed that it was that one. Does that make sense? Okay, minor arcs usually are named with 2, but it is possible they could give you 3, just to make sure you go the right direction. That would be the measure of AE plus the measure of ED. So what is the measure of arc AE? $63. What's the measure of arc ED? 90. Add them together, and we have the measure of arc AED. Okay, try the other one. Go. So, arc ADB starts at A, goes through D, and ends at B. So it's a major arc. There's a couple of different ways we could find it. One would be to add up all the angles along the way. The other would be, as somebody already pointed out, that's a major arc, so it's equal to 360 degrees minus AB, which is 117 degrees. And if we do that, well, that's quicker. Okay? So 360 minus 117 would be 243 degrees. Now we could also add up all the angles along the way, which would be 63 degrees and 90 degrees and 27 degrees and 63 degrees, but guess what? You get the same answer either way. So it doesn't really matter to me, as long as you get the correct answer, which approach you decide to take. Okay? All right, so that just leaves us with one final thing to talk about, and that is the idea of arc length. Now, we discussed this in a previous chapter, and we actually simplified this equation. So the one your book uses here is saying we take that central angle, x, and we put it over 360, because that is the portion of the circle that we're trying to find. So we take x over 360, and then we multiply it by the circumference, 2 pi r. Now, you can use that equation, or you can simplify that as we did in the previous unit to x over 180 pi r. Either one of these equations will work. It doesn't matter which one you use. Okay, they both work just fine for arc length. So, on this page here, this is the last slide, by the way, all we really need to do is come up with the arc length of zy. Notice that in each problem they've given us a central angle, which is going to be the x in our equation, and they've given us a radius. So all we're doing here is finding arc length using one of our 2 equations. And I will do a couple examples, so I'll do one example with each at least, so that you can see that it does not matter which one we use. So the one your book gives you is x over 360 times 2 pi r. So that would be, in this case, 75 over 360 times 2 times pi times the radius, which is 4. So we feed that to our calculator. Be very careful typing it into your calculator. 75 over 360 times 2 times pi times 4. And it's going to give us an exact answer of 5 pi over 3 inches, which is fully acceptable. You could also, and the directions do tell us that once it's converted into a decimal and rounded to the nearest hundredth, 5.235 would be rounded to 5.24 inches. Okay? On the next one here, I'll use the other version of the arc length equation, which is x over 180, where x is the central angle, times pi times r, which is the same exact equation. Again, they've given us an x value and an r value. Notice that the only difference between A and C is the radius. The central angles are the same, and we're not going to get the same answer. So please make sure you're doing this every time. Never assume anything. Okay, so 75 degrees over 180 degrees times pi times 6. So again, we're going to feed that to our calculator. 75 over 180 times pi times 6. And that will give us an arc length of 5 pi over 2 inches. Convert that into a decimal and round to the nearest hundredth, 7.85 inches. Okay, again, the directions specify that we're supposed to be rounding to the nearest hundredth. All right, on the last example here, just for fun, we'll do it with both equations just to show you it does not matter. Our x is 130 degrees, and our r, well, that's the tricky part. They gave us a diameter, so the radius would be the diameter divided by 2, or 10 divided by 2, so the radius is 5 centimeters. Please watch that. Don't use diameter in an arc length equation because it is not set up for diameter. So what we do here is we'll do it first with the one in your book. Arc length equals x over 360 times 2 pi r. That would be 130 over 360 times 2 times pi times 5. So 130 over 360 times 2 times pi times 5. Feed that to your calculator. We get an exact arc length of 65 pi over 18. Convert it and round to the nearest hundredth, 11.34 centimeters. I should have said centimeters there as well. Okay, now if we used the equation from last unit instead, x over 180 times pi times r, we're going to find out that we get exactly the same answer. It does not matter which version of the arc length equation you decide to use. So 130 over 180 times pi times 5. Hey, look, same exact answer, 65 pi over 18 centimeters. Again, that's 11.34 centimeters. Okay? So again, it does not matter which version of the equation we use. We get the same answer either way. Okay, that's the whole point of us doing it that way. That's it for this lesson. Thank you very much for your time and attention. Good luck on your homework.